My name is Matthew Graham, and I'm the ZTF project scientist. And in this brief talk, I'll give you an overview of what a night and what a year in the life of ZTF are like. So this is giving you the nuts and bolts of what the ZTF is like, following on from Sri Kulkarni's introduction and overview of the motivation behind ZTF. So this is what ZTF actually looks like. We're looking at a picture from the mirror, looking up the tube of the telescope, the 48-inch at Palomar. You can see our mechanical shutter at the end, which is about the size of a small table tennis table and can open up and close in about half a second. This is the actual ZTF camera, and you can see the 16 CCDs. And this robotic arm is our filter exchanger. And so what happens is that there is a little slot on the side of the telescope, which has 2 or 3 filters in it, a G, an R, and an I filter. And when we need to do a filter exchange during a night, we move the telescope into a safe position because Southern California is an earthquake zone. And there are people who get nervous about robotic arms doing things above expensive pieces of glass in an earthquake zone. So we move to a safe stow position and engage the robotic arm, which takes off the old filter, puts it into its appropriate slot in the cabinet, moves and grabs the new filter from its new slot and puts it back on. And you can see there are 3 sensors here, which are magnetic latches. And then there are also 2 physical latches on the device, so that the filter actually latches into place and is held by both electromagnetic coupling and also physical coupling, so that this is redundancy in case of the magnetic catches failing. It would still be held in place by the physical latches. And that's how we exchange a filter on ZTF. The whole process, as you can see, takes just about a minute, and the whole slewing to the safe stow position, changing the filter and slewing back takes about 2 or 3 minutes overall. So this is obviously not something that we want to do too many times during the night, because it loses us observing time, but it's something that we can do several times a night. And actually this whole filter exchange system has been tested, 500,000 times at least, or has done 500,000 observations at least, or 500,000 runs. So it's very, very highly tested. The same is true for the mechanical shutter at the end. And actually, it turns out that it's this mechanical shutter at the end which has provided greater problems over the past 3 years of ZTF than the more complicated robotic arm. So that's what ZTF physically looks like inside the telescope tube. We have 3 filters. As I said, we have a G filter, an R filter, and an I filter. And because of the way ZTF is funded, that we get 50% of our funding from the NSF and 30% from the ZTF partnership, and then 20% from Caltech. That is how ZTF observing time is divided up. So 50% of ZTF observing time goes to a 2-night public survey using the G and R filters of the northern sky visible from Palomar. 30% of the time goes to partnership programs, which can use the G, R, and I filter, because the I filter was provided in ZTF1 by the partnership. And those are of particular areas of sky at a higher cadence, or the whole sky in I every 3 or 4 nights. And then Caltech gets 20% of the time for the GNR filters, again for its own set of programs, which are allocated on the basis of applications for telescope time, in the same way that time on the 200-inch and Caltech Keck allocation works. So as I say, we have the 3 filters, G, R, and I. These are their theoretical curves. Yep, okay. Now, data is taken from the 48-inch and beamed via microwave link to San Diego in real time. and then it travels by internet to IPAC, where it's ingested into 3 separate pipelines. So we have the first pipeline is a basic image reduction pipeline, where we do standard calibration, flats, biases, all that sort of thing, and then on a single image, a source extraction algorithm is run over it, and individual magnitudes are measured at the positions of identified sources. And that gives you a single epoch catalog. And that's what goes into our archival data releases. Our archival data is the summation of all those individual epoch catalogs. And that's where the light curves that are the basis for a lot of our variable science come from. So that's just sort of straightforward source extraction algorithm run over one of the images. We have a second pipeline, however, which is what feeds our real-time transient alert stream. And this is where we do difference imaging. So we have built up a master image of the whole sky. So ZTF uses 2 fixed field grids divided up into the sky into pointings, where there's sort of minimal overlap at the equator, but obviously there's more overlap as you head up to the poles between neighboring field grid positions. And each of those has a reference image, which is built up from typically 15 to 20 good images of the sky for that particular region on sky that we've put together over the last 3 years. Typically, you need about 60 images to get the 20 good images. And so, it tells you that if there's a reference image available for a particular region of sky, there's probably a light curve for any object there, which has got at least 60 data points in it. But what we have is, so we have a reference image. So we have the science observation that's just been taken. We have the reference image, and we have a pipeline then, which takes one away from the other to give us our difference image. And we then run a source extraction algorithm again over that to look for all significant residuals. So anything essentially above a 5 sigma detection. And we consider those then to be transient candidates. There is then some filtering that's done on those to remove the things that are quite obviously data processing artifacts or not real. But that still leaves about 1,000 transients per pointing per field. And if you think during summer we get 500-600 pointings per night, in winter we get 1,000 to 1,100 pointings a night. That means that we're generating somewhere between 500,000 to 1 million transient alerts per night. We have a third pipeline, which is a moving object pipeline. And this uses all the available data and looks for streaks in the data, which might be caused by any moving object, whether it's artificial or natural. And the natural ones get reported to the Minor Planet Center to improve orbits or to confirm that it's a new object. So those are the 3 pipelines we have. It takes about 30 minutes for an observation to be taken from Palomar to go through the pipeline and to produce the set of transient alerts coming from it. So it's about median 30 minutes that the announcements of new detections of things that have changed or have moved is put out to the community. In terms of data volumes, if we assume, let's assume a mid-range night, it's about 8 hours 40, so we'll get about 700 observations on the sky. That produces about 1 terabyte of raw image data. Once that's been processed, that gives us about 4 terabytes of data products. As I say, somewhere between 100,000 and 1 million 5 sigma alerts. We can reduce that down to a number that are really useful, that we believe are real. Similar number of unvetted streaks from the moving image pipeline, which will give us, somewhere between 100 and 1,000 vetted streaks credible detections of asteroids or comets, or whatever, to be reported. And over the full, ZTF1 survey, which ran from March 2018 to the end of September 2020, first phase of ZTF, we have, as it says, about 3.2 petabytes of data. The reference images make up about 60 terabytes. The catalog, single epoch catalogs, makes up about 50 terabytes, of which we've got sort of almost 300,000 individual single epoch catalogs. We have 800 billion single epoch source measurements, and that gives us, with using PSF fitting, and we also do aperture fitting, and we have a smaller number, which is about 230 billion for those. So that just gives you some idea of the scope of volume that we deal with the ZTF data, both on a daily basis or a nightly basis and an overall basis. We can continue with the sort of overall statistics that we are dealing with. So we had 921 nights in ZTF1. Data was taken about 80% of them. We lose 20% rather to weather and occasional problems. Almost 500,000 exposures. We surveyed 22.5 million square degrees of sky. That's the same area of sky that LSST will cover in its 10-year mission. Obviously, LSST goes deeper, but we've covered the same amount of sky. In that time, we put out 300 million alerts. About 6.5 million of those were associated with known solar system objects. We did 6 monthly data releases in ZTF1, covering, there's a proprietary period on the partnership and Caltech data, but not on the public data. And so the idea was to try and get the public data, the image data and the catalogs out as quickly as possible. The alerts, of course, come in real time, and lots of science publications just by ourselves on those. This gives you some idea again of those 929 nights. As you can see, we had one period in October 2018 when we had a cryocooler leak. There's some oil that got into one of the cryocooler heads, and we actually had to bring the camera, take the whole thing off the 48-inch, bring it back to campus, and work on it for about 3 weeks to clear out all the oil and whatnot, and make sure everything was nice and clean and no further contaminants, and take it back. And that's the only time we've had to do that over the last 3 years. We're seeing the effects of climate change as well. Normally, we would not expect February to be a particularly dry month, but February 2020 turned out to be the driest February on record, so we got observing time then. And then we had them followed that with the wettest March in 25 years, and so didn't get any observing last March. But February and March 2021 have turned out to be dry, which is not great for everything, but it means we've had good nights observing then. So let me talk about the alert package that we send out. So as I say, maybe a few 100,000 to several 100,000 a night. It's a binary data format. It's about 70K per alert packet. LSST will be working with, I think, 80K. So in the binary format, this Avro format, we have 3 thumbnail images. It's a 63 by 63 FITS format image of the new transient, the new science image, the reference for that particular region of sky, and then the difference image. So you can see what the residual is and what the source extraction algorithm thought was the real transient. We include a 30-day rolling window light curve history. At the moment, that includes detections and upper limits. We are moving to change that over to forced photometry, which again will make it more like LSST. And then there's a whole slew of other metadata that's included in the alert packet. Parameters from various bits of the pipeline, the alert identification, the basic calibration, things like that. We have some machine learning algorithms which we run and put a score in there. That's the real bogus score and the star galaxy score. So it tells you, is this does this thing look star-like or galaxy-like? Does it look like a real alert, or do we think this is some sort of artifact? We put the distance to the nearest 3 pan-star 1 sources because we calibrate to pan-star 1. We put in the nearest solar system object within 30 arc seconds, and some form of alert history. As I said, the packet size is somewhere between 70 and 80 kilobytes. Also, all alerts get a unique spatially matched name. It's this sort of telephone directory thing, ZTF, the year, and then a 7-letter string starting at AAAAAA and going forward. If there is an alert detection, so we got a new alert detection, we check the 300 million, has there been alerts associated in that particular region of sky within 1.5 arc seconds of the position of the new alert in the past 3 years? If there is, then we associate that new detection with that previous detection, and it inherits the name. So there may be an observation that's taken tonight in 2021, which was, maybe it's a variable star or some sort of repeating transient, cataclysmic variable going off or something like that. If it's happening within that same 1.5 arc second error circle, then you'll find that we'll get the alert that's detected tonight will be sent out with the ZTF 18 name, because the data is associated automatically with that original detection. This sort of shows that we are consistently putting out somewhere between 100,000 and 1 million alerts a night. 16 alerts per square degree, 750 per exposure, 750 to 1,000 per exposure typically. Obviously, in regions of high stellar density, we put out more alerts. Also turns out that when the seeing is really bad, we put out more alerts because there is a lot of junk gets in. And also when the seeing is really good, we put in a lot of alerts because we are, ZTF has the full width half maximum of a typical stellar profile is about 2 arc seconds. And so when the seeing is occasionally sub arc second or very close to an arc second at Palomar, we are subsampling the PSF, and so we are getting too many things associated with, we get too many detections. Scheduling, this is not just a simple 1 survey, 2 survey, 3 survey. In ZTF1, we had a 40-40-20 split. As I said, ZTF2 now is a 50-30-20 split. We had a lot of different sub-surveys. Some were time constrained. The observations have to happen at this particular instance of time on a given night. We had deep drilling where we sit on a particular field and just observe it for an hour and a half or 2 hours, and that gives us 150, 200 observations. I should say our observations are typically 30 seconds, and then there's a 10-second gap allowed for slewing the telescope to the next position and for data readout. So we typically get 1 observation every 40 seconds. But the combination of all these different Caltech partnership and public surveys meant that we had about 90 survey configurations over phase 1 over those 30 months. And there was at least 3 changes, this one's coming in, this one's coming out per month. As I said, we try and minimize the number of filter exchanges we run on a single night. 30 months, we ran 4,000 filter exchanges roughly. So, 30 months is about 1,000 nights, as I've said. And so you're looking at about 4 filter exchanges a night on average. And target of opportunity observations as well. ZTF is not only a discovery engine in its own right, it can be used as a follow-up facility, particularly for things like LIGO. So in LIGO 03A, or LIGO 03 rather, we responded to a lot of the LIGO triggers, particularly if they were identified as neutron star, or neutron star black hole mergers. And then ZTF starts tiling with its 47 square degree field of view, the LIGO, the 1,000 square degrees of LIGO error volume, or that sort of thing, to a greater than normal depth than we would normally do. So the 30-second exposure from ZTF normally gives us about 20.5 as our 5 sigma detection limit for magnitude. But we can go to with a 90-second or maybe a 300-second exposure and then go to 21.5 or 22 in a single image. We can also co-add our 30-second exposures together to go to additional depth, but then you lose the time resolution. Well, what we can show is that the scheduler written by Eric Bellum at the University of Washington, who's our survey scientist, was pretty much on track on keeping for the Northern Sky survey, which was the regular 3-night cadence survey that we ran in ZTF1, and I say we're doing a 2-night cadence survey of the visible sky now in ZTF2, and then also a nightly galactic plane survey that we ran in ZTF1. And so even though this is a complicated setup, the automated scheduler worked pretty well. This is our sky coverage to the end of spring this year. You can see, yes, we cover pretty much anything north of deck -30 in G, R, and I. We have some areas where we have sort of 3,000–4,000 observations. Some areas where we have maybe a much smaller number in I. But it gives you, we have coverage for all the sky practically. Our reference images, as I say, these are the things that where we'd take a stack of about 15 good images, 15, 20 good images. You can see, and the reason why you're seeing 2 sets is what the top one is field grid 1, the bottom one is field grid 2. Remember, we have these 2 slightly offset field grids so we can get sky coverage totally. Again, you can see our reference images go to, well, let's say 22.5, 23, which means that this is very good for identifying very faint transients and things like that. That again just demonstrates we have a set of reference images that we use specifically for target of opportunity observations, because they may be doing a 300-second exposure, and that single exposure may take them to the depth of the regular reference images. We have a deeper stack of reference images that we can use for target of opportunity observations, which go slightly deeper. They may be sort of hitting 23, 24 as their limit. And so therefore are still viable as a deeper reference image to use for the purposes of subtraction and identifying faint sources in the residuals. Finally, our data releases, as I said, originally we were doing 6 monthly. We've now moved to as of the end of June this year, to a bi-monthly release cycle. So every 2 months from here on out, we release all public data that's been taken up into 2 months before. So at the end of this month, we'll be releasing all data that was taken up until the end of June. Then there's only ever an 8-week sort of period. What I mean by the data here, this is when the catalogs and the images from the public time observations become available. As I say, the transients are coming out every night. We also have a proprietary period of 6 months on our private data, 18 months, sorry, not 6 months, 18 months. So the data release at the end of this month will have all the data through to the end of February 2020. And, billions and billions of sources in there, 3.5 billion light curves, time series, including almost 2 billion, which have got more than 20 observations. So those begin to be good for doing very large statistical searches for all sorts of variable phenomena and such. And those are all available through the URSA interface and the ZTF query Python module, which I'm hoping you're going to be using this week, will allow you to pull over those images and those light curves, those time series, if you want, and things like that. So that basically is what both a night and a year look like in terms of data processing, data volumes for ZTF. And I'll leave it there. Thank you.